Good afternoon, everybody. So yeah, I'm going to talk a little bit about how we can use distal ash deposits to unravel the eruptive history of really active volcanoes like Aso in Japan. So East Asia and Japan in particular is obviously a super volcanically active region with over 130 volcanic centres across the arc of Japan. And some of the most active centres are actually in the south, down here, including Kikai, Ata, and Ira, and Aso here in the central range here. And they've been responsible for some of the largest eruptions, many of which were VEI 7 and 8. Yeah, you can see deposits of these massive eruptions all across Japan from the prevailing winds across the arc. And many of these deposits have been mapped really well by pioneers like Mashida and Arai, who have produced this excellent atlas where they've mapped all of these deposits across the islands and also across many of the marine cores in this region. And the ash from the AT eruption at 30,000, you can see here, has a visible ash extent right the way up to Russia and Hokkaido, and really quite thick. So Aso itself is quite a large caldera, around 25 kilometers north to south, and around 50,000 people actually live inside the caldera, with several towns, villages, highways, and railroads. And the caldera itself is formed from at least 4 really large VI 7-8 pyroclastic eruptions, known as Aso 1, 2, 3 to 4, with the ages mapped on here for you. But even these big events, the eruption history is actually really poorly constrained. And the tempo and the dispersal of events between these large events is even more poorly constrained. And this comes from typical problems that we've already heard in some of the other talks as well, because of the sheer number and magnitude of these events, and they often bury or destroy evidence of some of the older events, making it really difficult to use some of these proximal stratigraphies to reconstruct their eruptive histories. Access to these stratigraphies can be very difficult because of these really large, thick deposits. And of course, it's sometimes quite difficult to separate different eruptive events if you don't have clear paleosols, and it's quite difficult to get a really nice constrained age on some of these older events. So a study by Kiyosugi et al. In 2015 looked at the record that we have at the moment from Japan and did a statistical analysis of the volcanoes in Japan, and found that around nearly 90% of VEI4s are yet to be reported at around 100,000 years. So there's a lot that we don't know, even in Japan, where we've got a really long history of trying to unpick the volcanic histories of these centres. And so the case I'm making really is that high resolution records in distal realms are really key to pushing this understanding forward and kind of identifying and pulling apart events in these records. And here's just an image to kind of show some of the post-caldera forming stratigraphy over 100 meters thick near the rim of Aso. So the record that I've spent some time looking at is Lake Sugetsu. So this is a really high resolution paleo-environmental record situated in central Honshu in Japan. And it also has a long history of research, and the lake has been cored numerous times. And it's quite famous because, like Monticchio, it's annually laminated between 10 to around 60,000 years, and has a huge number of radiocarbon dates, so over 800 radiocarbon dates through the sequence, and forms part of the radiocarbon calibration curve. So when we find ash layers in this sequence, we can provide a really nice, precise chronology for the events. So here's just a picture of some of the varve sediments here. And the lake itself is part of a 5-lake system, and it's quite unique because the main inflow is through the Hasu River into Lake Makata, where you see a lot of the coarse sediment preferentially deposited. So only fine sediments really make it into Lake Sugetsu, where it's captured. And as I mentioned, there's actually over 30 visible thick layers through the sequence, providing a really nice detailed record of explosive volcanism from Japan and also further afield, so from China, South Korea. And the AT eruption that I mentioned earlier is over 30 centimeters thick, so there's some really nice thick layers in there. So our group has also spent some time looking for some potential non-visible tephras within the sequence. So these are commonly known as cryptotephras, and they just are tephra layers that contain much lower concentrations of volcanic glass. So they're not visible with the naked eye in the sediments. So we need to use a density extraction procedure to identify where we see peaks in the glass. And in the Holocene, this was really successful. So we found 16 additional cryptotephra layers over 3 or 4 visible layers. And we were able to extend known dispersals of some of the well-known eruptions in this area, and also help improve the chronology where we find historical ages, where we can import them into the age model. So in order to find cryptotephra layers, you can take samples continuously through your sediment at a low resolution, such as 5 centimeters or 10 centimeters. And where you find a peak in volcanic glass, you can go back and sample at a high resolution to refine your stratigraphic positioning. We'll typically count the shards per gram of sediment, and the volcanic glass is around 30 to 80 microns in size. So if we have a look at the Sugetsu stratigraphy just prior to this large AT caldera forming event from IRA, so this 7,000 years here, I'll show you the shard count. So the grey bars are the 5 centimeter low resolution samples, and the blue bars are 1 centimeter samples. And it's just cutting off the bottom there, but that is the concentrations of glass shards. But you can see there's numerous peaks over this 7,000 years of sediment, showing that there are other primary ashfall events reaching this lake. And we can be sure that these are primary deposits using several different methods. So you can see that the profiles of the inputs are, as we would expect, a nice sharp lower boundary where you see the ash falling on the lake, and then kind of a tail off as the shards are no longer washed in from the local environment. And we can also use the glass chemistry, so where we see unique chemistries, we know that it's not a reworking event. Also look at some of these in thin section as well, and they're really perfectly preserved. So this thin section has cracked where the cryptotephra is, but it's only 200 microns in thickness within the sediments. So going back to the stratigraphy, within this section, we see a really nice record from Asso in the lake. So these are just highlighted there in blue. So within 30 to 50,000 years, we see 21 ash layers. So typically 5 times more than there are 5 times more cryptotephra layers than the visible ash layers preserved in the lake. And the glass compositions are able to correlate these really well to specific eruptions and their source. So within this period, there's 8 from Asso, which are marked in blue. I've just showed here some of the geochemical fields for some of the volcanoes in Japan. And you can see here that Asso has a really wide compositional range, but quite distinct from the other centres nearby. And you see that the compositions of the glass range from quite mafic to intermediate or silicic, and sometimes span the entire range, typical for asso-caldera forming events. And using the volcanology of the lake, we can separate different pulses of activity from asso. So we can see that there are different phases of activity separated by around 3 centimeters of sediment, so about 50 years apart. And we can pick up these periods of increased activity between 35 to 30,000 years, so just prior to the Ira caldera forming event, AT event. And the next step is then to try and pull that back to the proximal stratigraphy, see if we can kind of use these chemistries to tie into the stratigraphy that's known at the source. That will be the next step for us, really, trying to see whether we can, compare whether the thin soils and that if some of these units have actually been grouped as events. So in summary, distal sedimentary records can be used to really augment and refine the eruptive histories of volcanoes. So this record is over 500 kilometers away from Asso, and we can use the cryptotephra layers to identify events between some of the caldera forming cycles. And I think this is key to really identifying some of the lower magnitude VI4-5 events that we're currently missing from our records. And we're able to cross-check the chronology and establish new dates using the age model from the site. And we're able to hopefully integrate the stratigraphies from this region and work out which layers can be used as chronological anchors to tie other paleo-environmental and archaeological records in this region. Yeah, that's everything. If you want to read more, this is published in this GQ paper here. Thank you.